Hypothalamus artificial intelligence, HI. Digital transformation powered by real-time autonomous and intelligent algorithms. Presents its artificial intelligence solutions for oil and gas state estimation. Kalman Filter. Part 1. Kalman Filter Framework. High Value Added Proposal. 50 years developing and implementing highly complex mathematical models, optimization systems and support systems for decision-making at enterprise scale. HI have developed a robust library of successful algorithms for application development and use cases across large global enterprises. With applications in general industry, energy, oil, gas, mining, agriculture, transport, finance, education, and regional planning. 80% of our process and development is executed by artificial intelligence agents, which ensures approach and implementation, at least 1,000 times faster than an army of engineers. Our solution is universal, it is standardized, and it is easy to adapt and implement, satisfying the demands of digital transformation 4.0. Our methodology is based on artificial hypothalamus framework, and use autonomous distributed real-time optimization. It allows algorithms to evolve, generating self-learning processes and being organized, minimizing human intervention, and our solution and value proposition allows for an average 10 to 15% reduction in operating cost, and/or an increase in profits. Kalman Filter applications in oil and gas industry. Artificial brains, integration of artificial intelligence and mathematical programming, are the result of HI's research in disruptive mathematical modeling methodologies for Industry 4.0. And they are the basis of the computational architecture of our technical proposals. For more information, those interested are invited to watch the video. Artificial brains, artificial intelligence and mathematical programming integration. Numerical simulation model of the digital twin. It corresponds to the physical model that exactly reproduces the behavior of the piping and pump system, that is, the flow of different types of products in the different sections of the pipes, and of the operating conditions in the pumping stations, for each pump configuration pattern, in series and/or parallel, for each type of product, for any pump speed. This model is integrated as physical model to predictive analytics methodologies, specifically the Kalman filter, and basic model to generate the approximate model that is part of the optimization models. The numerical simulation model produces matrices, or tables, that are the reference of the exact operation of the piping system and pumping stations, and these tables numerically represent functions of the energy consumed as a function of pressure, flow rate, product type, ERA injection, ambient temperature, etc. Validate and correct advanced analytics models, mainly optimization models. State estimation, models the prediction of estimation of the variables that represent the state of the system. These can be pressure, flow, RPM, roughness, density, etc., and physical model parameters, estimation of the parameters involved in the equations that represent the physical system, and which are subject to uncertainty. It is considered that the appropriate methodology is the Kalman filter, FK, including some of its variations and extensions. FK is, perhaps, the oldest, and most robust, methodology of hybrid predictive AI. The numerical simulation model can be used to generate synthetic operation samples, as it is assumed to correspond to the exact representation of the system, and thus enrich the database, very useful in the case of young systems with few historical measurements. Prescriptive analytics. To optimize are required the following models. The operation, dispatch, of the pipeline, at least 1 or 2 days in advance. This implies a real-time operating model, whose planning horizon is divided into periods of hours, fractions, and which can be redispatched at any time, and The transport of hydrocarbons in relation to nomination, DRA dosage, energy consumption month by month. This implies a short medium-term tactical operating model, whose planning horizon is divided into periods of weeks, fortnights or months, and that it serves to adjust the pothole program, prior to the dispatch of the polyduct. It is considered that the appropriate methodology for these models is mathematical programming, también conocida como exact methods. The other optimization alternatives are discarded by not be exact, may produce unfeasible solutions, and they don't guarantee to get the optimal solution, they leave money on the table. The results of the models, mainly the real-time ones, must feed the databases of the SCADA system, or distributed control. The image presents the IT architecture of the proposed solution. The mathematical models will be analyzed later. The high methodology involves linking predictive and prescriptive artificial intelligence methods, to give rise to decision-making artificial intelligence. Uncertainty dynamic systems. State estimation approach. The Heisenberg's uncertainty principle for position and momentum tell us that there is a fundamental limit to how precisely we can know these values for a system. The uncertainty principle implies that it is in general not possible to predict the value of a quantity with arbitrary certainty, even if all initial conditions are specified. State estimation framework. State estimation, SE, has numerous applications in technology and engineering. Initially, the real-life applications were for guidance, navigation, and control of vehicles, particularly aircraft, spacecraft, and dynamically positioned ships. Furthermore, the SE is a widely applied concept in time series analysis used in fields such as signal processing and econometrics. SE also are one of the main topics in the field of robotic motion planning and control and can be used in trajectory optimization. The SE also works for modeling the central nervous system's control of movement. Due to the time delay between issuing motor commands and receiving sensory feedback, use of the SE supports a realistic model for making estimates of the current state of the motor system and issuing updated commands. Other field of SE applications is to forecast hydroclimatic variables. Predictive analytics models, forecasting. Based on hybrid models, model-driven plus data-driven, supported in state estimation methodologies, more specifically improvements and variations of the Kalman filter, KF. Overall, the minimum functions of these models are smoothing, filtering and forecasting of the viscosity value of the crude oil transported in real time at any point of the pipeline, taking into account that, on a daily basis, laboratory tests are carried out to establish the viscosity value that is being transported. This actual viscosity data is confirmed a day after the shot by analysts. Smoothing, filtering and forecasting of the viscosity value of products in real time, assuming that an inline viscometer is available. However, the measurement of this is not exact, but it maintains precision and allows you to verify the trend of the measurement. Identification of the operating periods during which, due to the quality of the product, density and viscosity, the dosage applied affected the transport of hydrocarbons. Given the characteristics of KF, smoothing, filtering, and forecasting of the value of the pipeline's operating variables at any point, using the pipeline's physical model, and smoothing, filtering and forecasting of the value of pipeline parameters, e.g., roughness, slope, etc., when it is considered that these may be subject to uncertainty. As a general rule, it is considered appropriate to use an extended Kalman filter, or a dual Kalman filter, to simultaneously estimate state variables, and the parameters of the equations. Data-based algorithms only consider the database of observations, historical or synthetic, to determine the dynamic prognosis of the physical process. Normally, the related professional is a data scientist. Model-based models are based on the numerical simulation model, which must be fitted by means of algebraic expressions, to be expressed as a system of stochastic differential equations, or finite differences, or finite elements. This requires an expert in the field of interest, in this case fluid mechanics, mainly in the transport of petroleum products. The integration of the two approaches gives rise to hybrid predictive analytics, which can be considered as the appropriate method, that takes advantage of the mathematical knowledge of the physical system, and historical information. The most well-known method, and most used, for more than 65 years, is the Kalman filter. The state estimate describes the system based on state variables, characterized by discrete, empirical probability distributions, and dynamic, empirical, probability distribution functions that evolve over time. On the other hand, the predictions that can be made with the state estimation methods cover the entire horizon of the period under study. Smoothing, predictions about the past. Forecasting, predictions about the future, and filtering, predictions for the present. In a system under uncertainty, correcting the past may be just as important, if not more so, than forecasting the future and estimate the present. Examples of applications of the Kalman filter in pipelines are system monitoring, parameter calibration, leak detection, and maintenance following PHM methodologies. Under the state estimation approach, an uncertain dynamical system, whatever it may be, can be conceptualized as consisting of two systems or components. Physical model. The system dynamics can be represented based on a set of differential equations, or differences, based on mathematical laws. Typically, these equations are referred to as the system model. The state in which the system is located is referenced by the vector of state variables, xt. The state equation, which defines the gradient of state variables, has a known structural function that depends on a set of parameters, beta t. The ut vector is related to control variables, which humans can manipulate to control the system. Observation model. On the other hand, a measurement system, which observes the dynamical system by the variable zt, is related to the state variables by a vector function ht. The vector function ht can directly measure state variables, or measure transformations of these variables. Additionally, this observation system can include multiple measurement systems, from different sources. Together, the two components make up what in artificial intelligence is called a hybrid system, which combines information from the physical model with measurements from the observation system. To build it, two types of knowledge are usually required. That of the field expert, in this case an aerospace engineer, or similar, and that of a data scientist. The traditional is to use models based on mathematical models of the system, or models based on the data. The construction of the state equations requires complex mathematical knowledge, and therefore they are not commonly used. However, without an observing system, these isolated physical models contribute little to the online estimation and forecasting of the system's trajectory. Data-driven models are much easier to build, but they ignore scientific knowledge of the mathematical laws that govern the behavior of the system. By integrating the two models, state estimation becomes a robust hybrid method, capable of producing the best possible results, in terms of forecasting the state of the system. The concepts of state estimation are applicable to multiple types of systems. A few are mentioned below. Vehicles guidance, hydroclimatic variables, satellite imagery processing, economic systems, mass consumer products forecast. The diagram presents the evolution of a dynamical system. At instant t-1, the value of the state variables is known, xt-1, using the equations of system dynamics, the value of the state variables in t, xt, can be estimated. Iteratively, xt plus 1 can be used to calculate xt plus 2, and so on. To control the system, control variables must be included. The state variables are observed through the measurement system, which produces the zt variables that are an xt transformation. To optimize the process, it is desirable to use the dynamic programming approach, which includes an objective function, usually the cost of running the system. Since optimization must be carried out in a planning horizon, which usually covers more than one period, all periods must be chained together, and an optimization problem must be formulated. The objective function is the sum of costs in all periods. Given the uncertain nature of the system, it is necessary to incorporate state estimation, to obtain accurate information of the state of the system, in probabilistic terms, and perform a stochastic dynamic optimization process. Kalman was best known for his co-invention and development of the Kalman filter, a mathematical linear algorithm that since its origins has been widely used in signal processing, control and guidance systems, navigation and control. Subsequently, the Kalman filter has been used in almost all sectors of the economy. And it can be considered the best hybrid methodology of quantitative predictive artificial intelligence. The approach for the state estimation, SE, is supported on a conception of the stochastic processes, where the random variables are clearly differentiated of the measures, being understood that the modeler has data of the measurement system, that may be different from real values of the random variables. Therefore, all available observations are considered as random variables, having their measure information, but which, by reason of the randomness of the measuring system, are subject of precision errors, therefore, assume them as deterministic induces errors. Moreover, there might be more than one measure for a random variable, obtained by different sources. Two types of noise, or errors, are considered in state estimation modeling. A typical case of application of the Kalman filter is related to the guidance and control of vehicles. Epsilon-t, errors due to the modeling of the system, reflecting the uncertainty of knowledge of functions, equations or parameters, that determine the behavior of the system that is modeling, and theta-t, measurement errors that come from the precision with which the random variables associated with the system are measured. The conventional statistical models only consider one type of error, mu-t, which integrates modeling errors and measurement errors, whereas the state estimation modeling differs clearly the two types of errors. This may be the principal advantage of state estimation modeling over the traditional statistical modeling. Typically, the system modeling error, epsilon-t, is totally ignored, since the method is concentrated on the error in observed data. The historical data is assumed deterministic. The conventional statistical models only consider one type of error, mu-t, which integrates modeling errors and measurement errors, whereas the state estimation modeling differs clearly the two types of errors. This may be the principal advantage of state estimation modeling over the traditional statistical modeling. Typically, the system modeling error, epsilon-t, is totally ignored, since the method is concentrated on the error in observed data. The historical data is assumed deterministic. And it's a big mistake. Uncertainty dynamic systems. Rudy Emil Kalman was a Hungarian-born American electrical engineer, mathematician, and inventor. Rudolf Kalman was born in Budapest in 1930. After emigrating to the United States in 1943, he earned his bachelor's degree in 1953 and his master's degree in 1954, both from the Massachusetts Institute of Technology. Kalman completed his doctorate in 1957 at Columbia University in New York City. Kalman was most noted for his co-invention and development of the Kalman filter, a mathematical algorithm that is widely used in signal processing, control systems, and guidance, navigation and control. For this work, U.S. President Barack Obama awarded Kalman the National Medal of Science on October 7, 2009. Kalman filter theory. In statistics and control theory, Kalman filtering, also known as linear quadratic estimation, is an algorithm that uses a series of measurements observed over time, containing statistical noise, and other inaccuracies, and produces estimates of unknown variables that tend to be more accurate than those based on a single measurement alone, by estimating a joint probability distribution over the variables for each time frame. The KF process has as its starting point the dynamic equation of state variables, which has as its input the a posteriori prediction in t-1, and the control variables in t. The result is the a priori estimate of the state variables for period t. Using the observation equation, KF produces the a posteriori estimation of the vector of measures zt. On the other hand, the system that is being observed, through the measurement system, produces the actual measurements. The comparison between the estimate a priori of zt and the real value of zt produces an error, or innovation, that is used to make corrections in the state variables. This is done by means of the so-called gain matrix, M, which is a central part of the KF. The result is the a posterior estimation of xt, which will be the starting point to carry out the process in the next period, t plus 1. We ignore the past as much as the future. Of the present we generally ignore where we are. The stochastic processes where the random variables are clearly differentiated of the measures allow the modeler to improve knowledge of the past based on the evidence of the present. It can only be realized by a combination of forward and backward processes. If T1 is the period for which you want to obtain the best estimator of the state variables, given the information received up to T. The relationship between T1 and T defines several types of process. Smoothing, T1 less than T, it involves predicting a posteriori the state variable in the past T1, before T. Filtering, T1 equals T, it involves the correction, filter, of the prediction of the state variables in T, while reaches the information. Forecasting, T1 greater than T, it involves the prediction of the state variables for periods T1 after the present T. The last two functions are the most used, however. The prediction of the past makes perfect sense when we recognize that in the past, we only had estimates of the state variable, because we never know its real value, which can be improved by processing the information coming later to T1. State estimation models assume that we ignore the past almost as much as the future, and for the present we have a rough idea of where we are. As we acquire information, uncertainty in all directions must decrease. The image shows the timeline of COVID-19 events in Hubei, China. The gray curve presents the actual status of the pandemic, and the yellow curve was reported by Hubei city authorities. It is easy to visualize the large discrepancy that exists between the two curves. In general, there is a delay in detecting what is happening. The gray curve may become known in the future, but it is not known at the time decisions are made. Therefore, decisions must be supported by the yellow curve, which is known to be incorrect. This situation is not the best, and it must be improved. This can be achieved using methodologies based on state estimation. Smoothing is fundamental in the process of estimating the epidemic state, because due to the type of process, it is necessary to reconstruct, in the best possible way, the history of the epidemic, since an inappropriate interpretation will give rise to bad decisions, since they are made based on measures that do not reflect the reality that is happening. That case happened in Hubei, in the early days of the pandemic. Then, in the case of the pandemic, predicting the past could be much more important than predicting the future. Variations and extensions of Kalman filter. Considering that KF is oriented to linear dynamic systems, an effective algorithm for identifying an industrial or a natural process may be considered as a combination of the following methodologies. Kalman filter, extended Kalman filter, ensemble Kalman filter, dual Kalman filter, Bayesian model combination, and multiple Markovian state Kalman filter. Multi-methodologies Kalman filter. The advantages of the approach based on the integration of multiples methodologies of state estimation versus the classical methods are presented below. One of the limitations in the modeling of uncertainty dynamic systems is that related to the hypothesis that the response function is known a priori, and structural changes of the system cannot be easily modeled. The response function of a system reflects the way its internal structure works. Structural changes cause changes in the response function and cannot always be expected. Many of the changes that occur in the behavior of a system are consequences of unexpected events. Before these eventualities, schemes based on multiple system states, or similar, to determine the moments in which structural changes occur, differentiating them from pure stochastic effects. From the point of view of control, the state estimation allows the online analysis of the phenomena that are occurring, while conventional methods are aimed at ex post analysis, to describe phenomena already past. Dual state estimation of state variables and model parameters. When the true value of the parameters, of dynamic the equation of state variables, is unknown, it is necessary to use a variation of KF, like EKF, the value of system state variables when the structure and parameters of differential equations are known for certain. Extend Kalman's theory to systems of nonlinear equations. NKF, It is a recursive filter suitable for problems with a large number of variables, such as discretization of partial differential equations in geophysical models. The NKF essentially replaces the covariance matrix by the sample covariance. DKF, it uses two filters that act in parallel, one on state variables, and one on parameters of a statistical model, or of the physical model, and UKF, it belongs to the particle filter, PF, methods that are recursive implementations of Monte Carlo-based statistical signal processing. When the true value of the parameters, of dynamic the equation of state variables, is unknown, DKF uses two filters that act in parallel, one on state variables, and one on parameters of a statistical model, or of the physical model. Based on this approach there are multiple theoretical variations. Here will be considered the one presented by Labar et al. The diagram summarizes the process. The diagram shows the connectivity of the standard Kalman filter. The DKF includes an additional filter on the parameters, in order to simultaneously correct state variables and parameters of the dynamic equations. Like Herbert Simon, hypothalamus artificial intelligence believes that the computer-based mathematical modeling is the greatest invention of all times. Thank you for your attention.